trigger finger for Her Majesty. Another one with the
Hello and welcome to the practice problems video for Green's theorem. So during this video I'll be going over two examples. The first is quite lengthy, I'm just going to forewarn you, but it's very demonstrative of the concepts that we've been going over as far as Green's theorem. So in the first problem, number 1, we are basically going to verify Green's theorem. So as you can see here, verify means something different than prove. Okay, so prove would involve critical thinking and a lot of critical thinking and reasoning behind where the theorem even arises from, like based on other theorems and etc. and so forth. But verify just means given an example. So I'm going to provide you with information, and you just have to verify to prove that two sides of an equation are equal. Okay? So what we're going to do is, here's the given information. So we have the line integral over the closed curve, which is of xy squared dx plus x dy, where C, our curve, is the unit circle. So again, unit means 1 in some way. So in this case, unit circle is radius of 1. And this is oriented, I'll just say oriented counterclockwise. Okay, so it's already going this way. Alright, so that's our curve and our given vector field. So this is like our f sub 1, and this is our f sub 2. Okay. Alright, so what we have to do here is, as I said before, verify means show / confirm that both sides of an equation are equal. So in this case, Green's theorem says that the line integral over the boundary of your domain, D, so, sorry, that should be a 1, f sub 1 dx plus f sub 2 dy is equal to the double integral over the domain itself of partial f2 partial x minus partial f1 partial y, and then dA. Okay, so this is how we're going to approach this problem, is first of all doing this, the left side. We're going to solve for the left side, so that'll be the first part. The second part will be solving for the right side separately, okay? So we're going to start from scratch and just solve the second part. And the third part here, we're just going to show that they're equal. So the third part is going to be the easiest. We're just going to compare the answers, okay? So let's start off by doing part 1. We're going to do the, in this case, this is the direct line integral line integral. Okay, so let's do this part first here. Alright, so let's set it up on the next slide. So we have, this is what we want, is the line integral over the domain, or the boundary of the domain. Okay, and we have our f sub 1 dx plus f sub 2 dy. Alright, so our parameterization parameterization for the curve, which is the unit circle oriented in the counterclockwise direction, that's just going to be our x equals r cosine theta. So in this case, r is our 1 cosine theta, and y is 1 sine theta. Okay, and you can also use t here if you want for your parameter variable. It works the same way. And then our dx is then a negative sine theta d theta, and our dy is going to be a positive cosine theta d theta. Okay, and as for the bounds for our parameter variable, those will go from 0 to 2 pi, so you make it all the way around the circle, right? Okay, so that's how we're setting up our parameters, and now we can just plug in everything in here that we see with something in theta. Okay, so we're going to set up the bounds, so that's 0 to 2 pi, and then our f sub 1. So our f sub 1, just as a reminder, our vector field f was x times y squared, and then comma x, just an x there. Okay, so we're going to plug these in with things in theta. So for x, we're plugging in cosine theta. So that would be, oh, okay, just kidding, misplaced arrow bracket. So we're plugging in a cosine theta for this part here. So we have a cosine theta for the x, and then we have a y squared. This is our f1 and f2. Okay, and then a y squared. So y is sine theta. So that's squared, and then we have a dx here. So this will be negative sine theta d theta, negative sine theta d theta. Okay, and then we have a plus sign, and then we have to write our f2, which is x, but now in terms of theta, so that'll be a cosine theta. And lastly, our dy, which is then just cosine theta d theta. Sorry. Oop, there we go. Okay, so now we'll just simplify from here. So what we get is 0 to 2 pi, and then in the front is a negative cosine theta sine to the third theta, plus, I'm just going to write the d thetas at the end, plus a cosine squared theta and d theta at the end. Okay, so now I'm just going to separate these. So we'll have, I'll write this one in front first. So we have 0 to 2 pi, and then a cosine squared theta, d theta, and separating them with the minus sign here. 0 to 2 pi of cosine theta sine third theta, and then a d theta. Okay, so we are going to have to work with a little bit of trig identities. That's how it gets. This problem is a bit lengthy, but once you get familiar with practicing with them, then you'll get more comfortable working through them, and you'll be able to recognize things. So here, the cosine squared theta, we're going to have to use the relation, the trig identity, that 2 cosine squared theta minus 1 equals, this is a double angle formula, so cosine 2 theta. So cosine squared by itself is then going to be cosine 2 theta plus 1 divided by 2. Okay, so keep that in mind. Make a note of that, and I'll rewrite that on the next slide. So that's for this integral here. And then for this one, we need to do a u substitution. So I'll make our u be sine theta. And then our du is then cosine theta d theta. So d theta by itself, if we just divide the cosine on both sides, we get du over cosine theta. Okay, so we can substitute that in directly here. Okay, alright, so I'll move on to the next slide and we can rewrite these. Okay, so then we'll have on the first one, we had a 1/2, okay, and we're replacing the cosine squared, right? So with a cosine 2 theta plus 1, and then that was over 2, so this is the over 2 right there. Okay, so this is times d theta, and then minus, and we're going to do a u substitution here, so I'm going to remove the boundaries right now. But then we have a cosine theta, because we didn't have anything to replace it right now. Sine theta was replaced by a u, so that'll be u to the third. And then d theta was replaced by a du over cosine theta, which is very convenient, and we can cancel out the cosine thetas. Okay, so continuing, I'm going to break this down further by the addition sign here. So 1/2, 0 to 2 pi, cosine 2 theta d theta plus a 1/2 times integral from 0 to 2 pi of 1 d theta. And then here, we simply have a u to the third times du. Okay, so a lot of stuff going on at the same time. And again, problems like these can get kind of lengthy, as I've said before, and it's important to keep all the details straight, especially the minus signs and your factors of 2 and such things like that. Okay, so then here we can do a u substitution. So we'll make u be 2 theta, and du is then 2 d theta. So d theta is du over 2. Okay, so we're going to sub that in. So you get a 1/2. I'll remove the bounds for now, and we get cosine u, and a d theta is replaced by du over 2. So we have a factor of 1 over 4 here. Okay, continuing, we have 1/2 times theta, as theta goes from 0 up to 2 pi, and then minus, and we'll integrate, so we get a 1/4 u to the 4th. Okay, so I'm going to bring this 2 out and make it a 1/4. And then when you integrate the cosine u, when you integrate the cosine u to u, you get sine u. And then continuing again, we get 1/2, and we're going to plug in the 2 pi, the upper limit and the lower. And then we have a minus 1/4, and I'm going to replace this u with, remember u equaled sine theta here. So I'm going to replace that. So sine theta to the 4th. And now we can reinstitute our bounds, so that's 0 to 2 pi. Okay, so again, continuing, we have 1/4 times sine, and this time u was 2 theta, as theta goes from 0 to 2 pi. And then here in the middle, we get 1/2 times 2 pi, so that's just a single pi. All right, and then we're going to plug in our bounds here, so that'll be sine 2 pi to the 4th power minus a sine 0 to the 4th power. And as you might notice here, these last ones, these are both 0, so this last term is 0. And then we'll continue this on the next slide. Okay, so then we have a 1/4 times sine of 2 times 2 pi, which is 4 pi, minus sine times 2 times 0, or sine of 2 times 0, which is 0. And then get a plus pi, and then the other thing was plus a 0. And these, again, this is 0 and this is 0. So our final answer, using the direct line integral method, so on the left side, that turns out to be pi. Okay, so this is our first answer. Alright, so now we can start with the second answer, or the second approach, which is on the right side of the equation. So this is, I'll just nickname it the Green's theorem method. Green's theorem method. Or you could just think of it as the double integral over d, the domain. Okay, so what we have was this was our given, so xy squared dx plus x dy. So that means that our, as I've written before, our vector field is given by xy squared comma x, where this is our f sub 1 and this is our f sub 2. Okay, so for the inside parentheses thing, for this formula here, so we have our df2 with respect to x and the partial with respect to y, okay, and our dA. So for this part in here, let's figure out what the parentheses are. So we're going to take the partial with respect to x of x, which is our f sub 2, minus the partial of y with respect to y of f sub 1, which is xy squared, x times y squared. Okay, and then what we get here, so the partial of x is just a 1, and then we get minus, and if we're differentiating this with respect to y, we get 2xy. So our answer for that is 1 minus 2xy, so that's what we're going to plug in there, for the parentheses. Okay, so then this is how we set it up. So we're plugging this in for the parentheses, so we get 1 minus 2xy, and then a dA. Okay, so our domain, again, it is bounded by the curve, which is the unit circle. So you could think that our domain is the unit circle itself. So this is D, everything inside. Okay, so what we have to do is not parameterize it, but I was thinking polar coordinates would be the best option since it is a circular thing, and it's symmetrical about the origin. So if we switch into polar, so I'm going to switch from rectangular to polar. So this is a change of coordinates, right? Okay, so I'm going to switch into polar, and I guess I can write down here. So we have the relation that x equals r cosine theta, and y equals r sine theta, right? And for the unit circle, so it crosses at 1 on the x and y axes, right? So this is x and this is y. Okay, so r goes from 0 to 1, remember, to get everything inside this unit circle. And theta has to go all the way around the circle, right? So that goes from 0 to 2 pi. Okay. So now that we have these bounds for polar and these equations here, we can just sub in everything in terms of theta. Okay. And I will do so on the next slide. So for our bounds, I'm going to do theta first. So 0 to 2 pi. And then our r is 0 to 1. And inside we have 1 minus, we should have a 1 minus 2xy. But in polar coordinates, this is going to be 1 minus 2 times r cosine theta times r sine theta. Okay. And then we have our dA, which is actually r dr d theta. Remember, whenever you switch into polar, don't forget to use the r in front here. That comes into play. Okay, so now we'll simplify and simply calculate this double integral. So we get 0 to 2 pi, and then 0 to 1. And then if we simplify this, we get the factor of r here, r times 1, minus a 2 times r to the third, and then a cosine theta sine theta, and then a dr d theta. Okay? So now we're just going to integrate the inner integral. We're going to compute that. So we have 0 to 2 pi again. And if we are integrating with respect to r, we get 1/2 r squared minus 2 times, well, okay, I'll keep the constants, 2 cosine, I'll put these in front, so 2 cosine theta sine theta, and then we're integrating this part, so that would be a 1 over 4, r to the fourth, right? And then this is as r goes from 0 up to 1, and then we have our d theta sitting at the end there. Okay? So now we're just going to plug in, well, these cancel first of all, 2 and the 1/4 go to 1/2, okay? So then what we get is the following. So we have 0 to 2 pi, and then a 1/2 times, we're going to plug in the 1, so 1 squared minus, and then we have our factor of 1/2 from here, and then a cosine theta sine theta times 1 to the fourth. And then when we see how we have r's in both of the terms, so that means that when you plug in 0 for r, we're just going to get minus 0. All right? So now we can simplify a little bit. So we have this, and I'll just write it a little bit nicer. So then we have a 1/2 minus 1/2, I'll write sine theta, cosine theta, and then a d theta. Okay, so this is where we're at now. And I would like to break this up into 2 separate ones, and I'll do so on the next slide. So if I break this up, we get 0 to 2 pi of 1/2 d theta, and then minus a 1/2, I'll just take that out, of 0 to 2 pi of cosine, or I guess I'll write sine first. So sine theta, cosine theta, d theta. Okay? So for this first one, that'll be pretty simple and elementary. And then this one, though, we need to make one of them a u. So I'll pick u as sine theta. And then du is cosine theta, d theta. So d theta directly is du divided by cosine theta. Okay? So now we're going to do u substitution here on the second one. But for the first one, that just simplifies to a 1/2, and then theta, as theta goes from 0 to 2 pi. And then we have our 1/2, and I'm going to remove the bounds here, but we're going to replace it with, sine theta is now u, cosine theta, there's nothing to replace that right now, and then d theta is du over cosine theta, which is great, because then those cancel, and we're left with 1/2 integral of u du. So then here, we're going to plug in the bounds, so we get 2 pi minus 0 minus 1/2 times 1/2 u squared, okay? And then here we get just a pi, a single pi in front, and then we have minus 1/4 u squared, so that would be sine theta squared, as theta goes from 0 to 2 pi, okay? And now continue, we're almost there. So pi minus 1/4 times sine 2 pi squared minus sine 0 squared. And these again turn out to be 0. So we are left with pi as the answer for our second approach, which was the double integral over the domain. So the last part is simply saying, so from the line integral over the boundary of D, so when we did this part here, this yielded an answer of pi. Okay, so that was part 1, right? And then we had we just calculated the double integral over the domain of partial f2 with respect to x minus partial f1 partial y, and then our dA, and this also yielded a pi. This is from the second method. So the third part is just saying that these are equal, and we can do so by just saying that pi is equal to pi. So, yay! This means that we have verified Green's theorem. So, alright, great job. And now on to the second problem, which is a bit less lengthy, thankfully.
Another tricky little gun giving solace to the one that'll never see the sunshine. Another inch of your life sacrifice for your